Hello, everyone. My name is Lee Pucker. I'm the CEO of the Wireless Innovation Forum, and I'd like to welcome you all to the 11th in the Wireless Innovation Forum's webinar series. Today's webinar is entitled Techniques for Wideband RF and IF Signal Recording, and it's being given by Roger Hosking of Pentech. A little bit of administration before we get started. The slides that are presented during this webinar are going to be posted on our website. You can find them at wirelessinnovation.org/webinars, tutorials, and resources. And if you need that link again, just send me an email and I'll get you the information that you need. A little bit on the user interface that you have in front of you. If you look at your interface, you'll see that there's a little a button that you can click. By clicking on that, it'll actually minimize the interface and make it go back and forth. Looking at your audio session, when you logged in, it automatically, the GoToWebinar interface automatically puts you in microphone and speakers. If you'd like to use your telephone instead, you can simply click the telephone and it'll give you your dial-in information and your access code. When you do it, be sure and you enter your audio PIN, and that is what attaches you onto the system so that I can unmute you if you want to ask a question later. Everybody right now is muted. If you would like to ask a question, there's a couple of ways forward for you. The first is to simply use the questions window. You can type your question in there. I'll receive the questions, and then at the end of the session, I'll ask the questions to Roger, and he can respond. Another way, when we get to the question and answer session at the end of the webinar, you can simply click the little raise your hand button, and that'll notify me that you'd like to ask an audio question, and I'll unmute your microphone to allow that to occur. So with that in mind, I'd like to introduce Roger Hosking of Pentech, and Roger, I'll turn it over to you so that you can get started.
Okay, thanks, Lee, and welcome to our seminar today. What we're going to do is go through some of the basic technology that's used in acquiring, digitizing, and recording wideband signals, typically for communications or for even radar applications. And what we're going to do is first start out with a basic view of what does a software radio recorder system look like. Usually what we'll do first is take the antenna signal, which is at the high RF frequency, and we'll go through an RF tuner, which down converts that signal to a lower frequency that we can digitize with an A to D converter. So the A to D converter then produces digital samples of the IF signal. We then typically go through a digital mixer and digital local oscillator to translate the digital IF signal to baseband. We filter it with a low-pass filter, giving digital baseband samples of the correct bandwidth according to the channel that you're trying to receive or record. Those operations, the digital mixer, local oscillator, and the filter, are traditionally called a digital down converter. We then take the digital samples either directly into a recording, like a hard disk, for example, or sometimes we'll go through a DSP stage, and then we'll go into the recording after the DSP is done as well. So this is an overall view of a software radio recorder system. If we turn it around and go to the playback system basically does everything in reverse. It starts out with samples that are digital baseband samples that come from either a DSP or directly off a hard drive. Those digital samples are interpolated. That means the sampling rate is increased to a higher rate, but the signal itself is preserved. We then go through another mixer and local oscillator using digital technology to translate the baseband digital signals up to IF digital signals, intermediate frequency, which then go through a D2A converter to analog IF, and then through an analog RF up converter to produce an analog RF signal frequency that then can be sent through a power amplifier to the antenna. So again, it's just the reverse, very similar operations, but just done in the reverse direction. So what we need to do is find a way to implement those operations that we just went through And there are a lot of challenges for high-speed recorders. We have so many different things to take care of when we're talking about the high-speed recorders, and some of the functions that you see listed here. For example, we've got to digitize and maintain the signal integrity. We don't want to degrade signal integrity. We have to capture with triggered operations often. We have to synchronize the capture across multiple channels so that in case of a phased array antenna, each antenna element is being digitized synchronously with the others. We have to eliminate bottlenecks in terms of data flow to the disk drives, to the storage, through the RAID controllers, which are the interface to the hard drives. We also have to eliminate overhead that's typically associated with operating systems. Taking care of things like buffering and latency issues all have to be solved. And then environmental issues, shock, vibration, all of these things have to be put together, integrated and engineered into a solution so that you really can ensure zero data loss. You want to capture every single sample that is coming in from the antenna. So how do we do that? We use a lot of advanced technology. At the front end, we use advanced, usually FPGA-based data acquisition modules like the one you see here that are in typically a PCI Express board or VPX form factor with A to D converters and D to A converters. Currently, we're operating with A to D converters that run up to 3.6 gigahertz, D to A converters that are 1.25 gigahertz. These devices have to do the synchronization and the sampling, and they also include hardware DMA controllers that move the digitized data across the PCI Express interface to the rest of the system. The rest of the system must be a very high-performance server-class PC or single-board computer with fast links. It needs to have a reasonably fast CPU. It has to have very fast memories and bridges and chipsets that allow the PCI Express links to connect up this board to the memory and to other boards such as the RAID controller, which is the interface to the hard drive. So we're using PCI Express Gen 3 often in the system motherboard, and we're using SATA 3 disk interfaces to achieve the rates that we need to across through the system. And then finally, we're using solid-state drives connected to the RAID controller to achieve a couple of nice things. One is a very high immunity to vibration and shock. And then secondly, we have some really nice read-write rates on each of these new drives using solid-state technology. We'll just take a look here, a quick look here at some differences between the older magnetic drives, which you can see a picture of right here. There's a lot of moving parts. There's a spinning platter. There's an arm that holds the read-write head that has to move in order to access the different sectors and tracks on a drive. Conversely, a solid-state drive is silicon. Okay, it uses silicon devices. There's no moving parts. The interface to the outside world, it looks exactly the same. So the interface itself makes the solid-state drive just look like a magnetic drive, typically with a SATA interface. But let's compare some of the characteristics between the magnetic and solid-state. And so we're going to first look at ratings here in terms of, for example, capacity. So the capacity of a magnetic drive is higher than a solid-state drive, given a typical high-end devices. The read rate and the write rate on solid-state drives is higher. In terms of size, weight, and power, you can see that the solid-state drive really takes the prize with some significant reductions in all three of those categories. Also, in terms of shock and temperature, solid-state drives really come out ahead. Now, we get down to some parts where the magnetic drive scores ahead, and that's in cost. It is lower in cost. It could be 5 or 10 times lower in cost per gigabyte. And you can see that here we've got a cost per gigabyte that shows roughly about a factor of 20 in the cost per gigabyte. And the other thing about the solid-state drives is that they do have a finite number of write cycles. They have a finite number, so that in the processor that's part of a solid-state drive, you have what's called a wear leveling algorithm. And what that wear leveling algorithm does is it spreads the number of writes around to even out the number of writes that any particular memory cell experiences. However, each of these different algorithms varies from manufacturer to manufacturer and from SSD type to SSD type. So each type of SSD must be fully tested and characterized to make sure that you can use them for the sustained read-write performance that we need in the real-time recorders. Let's take a look at the system flow. How do we actually move data through the system? Well, we start out with high-speed A to D or D to A module that has a DMA controller connected to it, and we have a RAID controller that's connecting, again, through a DMA channel to the solid-state or magnetic disks over SATA links, and connecting the analog I.O. module. What we're doing is using PCI Express links, first between the I.O. module and system memory, and then between the system memory and the RAID controller. So all of the data flows directly through and across these hardware-controlled DMA links that use PCI Express to achieve the speed that we need for the operation. We do have a system CPU and operating system that's managing everything, but they do not touch the real-time data. They're simply there to initialize the DMA controllers, the RAID controller, and the I.O. module, and manage the performance, the overall performance, through interrupts. So it's an interrupt-driven management facility that the CPU does, but the data itself is not touched by the CPU, and that's how we can achieve real-time operation, even using a non-real-time operating system. So in order to bring all this technology and the architectures we've talked about, we've come out with a product line which we call Talon, which is our trade name for Talon recorders. They are high-speed recording instruments, complete systems that will do both analog and digital recording. You can program them for different bandwidths and tuning frequencies in case of the analog device, analog instruments. They're ready to use out of the box. They have intuitive controls. You don't need to do any software development. We have 3 different classes of environmentals, form factors, commercial, rugged, and extreme. We'll look at those in a little bit more detail later. It's based on a Windows 7 operating system. So it's really a complete workstation that surrounds the real-time recording function. We manage all of the interrupts and the data flow through a software tool called System Flow, which includes both an API and all of the operating software for the recorders. And the last important point is that all of the recording is done through NTFS files. What that means is that immediately after the recording is made, you can open up that file with any Windows application for signal analysis or archiving or sending across a network. So in the first case, the RTS commercial brand of Talon are intended for commercial environments. They use magnetic drives where you get the maximum storage capacity, but they're lab-based or office-based environments. They're air-cooled, and they come in different form factors where you can basically have different size chassis, typically a 19-inch or a 26-inch deep. All the drives are removable so that they can be hot-swapped and replaced. In case you need a longer recording, you can take out the full drives and put in empty drives and continue with the recording. The second class are the Talon RTR, stands for rugged recorders. And here, in these devices, we use exclusively solid-state drives because they are intended for tougher environments where shock, temperature, and vibration come in. They're still air-cooled, and they're very suitable for things like pressurized aircraft cabins and moving vehicles. Different form factors are available. Most of them, again, are in the rack mount form factor, but we also have, as you see in the lower right there, we also have a portable briefcase-style chassis where this device can actually be taken out into the field on a vehicle or in an aircraft. Even during vibration, this instrument then can record real-time data by virtue of its construction and by virtue of the fact that we have the solid-state drives that are not subject to those vibrational effects that magnetic drives otherwise would be. And finally, the RTX, this is the extreme family. These are intended, again, for the most extreme environments where you have typically a sealed, conduction-cooled chassis. This would be suitable for unmanned vehicles, for torpedoes, unpressurized cabins, and so forth. Of course, here we're exclusively using the solid-state drives, and typically they will come in a conventional type 3U VPX backplane, let's say, with a half ATR style chassis. So those are the three different classes of Talon recorders. Now just taking a look at the system flow software architecture, we have the client part of the system flow is shown over here on the left side of the screen, where you have the user interface. You have the graphical user interface, you have the signal viewer, and so forth. And we have a server side of the software, which is over on the right side of the screen. This is where the real-time operation is done. And so the client-server division of labor, if you want, makes it very convenient for us to keep the server software very hard real-time and allow different clients on the left to have different operating systems, Windows, Linux, or another operating system. To make the connection between the client and the server, we have defined and offer as part of system flow an application programming interface, or API. So we have written our own client as kind of an example of how to use the hard real-time server functions of the recording and playback. And you can use our client, or you can write your own client and take advantage of the real-time operation of the server. For example, you might have a client installed on a cockpit computer in an aircraft, and you might have a server installed in an equipment bay, down in an unpressurized equipment bay, let's say somewhere else, with a connection between the two via Ethernet. In this case, the API would be controlling every aspect of the real-time operation that's taking place in the 3U VPX chassis that you see here over the Ethernet connection, where the displays, the controls, and everything are done in the cockpit. So it makes it a very, very nice way to manage these types of systems. We take a look at the Pentec client interface. It's a Java-based client GUI, and it's really a very intuitive push-button operation. We have recording and playback client functions that are on screens that you operate with a mouse and a keyboard. We also have a convenient utility, which we call our signal viewer, that allows you to look at signals before, during, and after the recording. So, for example, one of the screens that comes up are the parameter screens for setting up your input channel. In this case, an analog input channel where you'd set the bandwidth, decimation, the source, triggering modes, polarity, sampling rates, and so forth. This can all be set up and configured just by entering the parameters or pulling down selections. You click Apply, and then you're ready to go on to the next channel setup. We also have a very intuitive recording screen. Here you see in the lower part of the screen, you see this happens to be a 3-channel A to D converter. You specify the file name. You specify the transfer length in megabytes or in seconds. You click the record button. It starts the recording. You can see progress here, both in the speed of the recording. There's an indication of data loss. We also allow you to click on the master record select buttons, and then up top you can trigger with one master record operation. You can have simultaneous synchronous recording of all the channels below that you've selected to be controlled by the master. So very intuitive, very easy to use. If we go to the playback screen, again, very, very easy to use. What you do is specify the file name, the starting position in the file you want to play back, the transfer length in seconds or megabytes, and then you simply hit play. In this case, what we would do is fetch the file from the solid state or the magnetic disk and send it out through a D to A converter to reproduce the analog signal that was recorded. We also have a very nice signal viewer that allows you to look at the signals that you're about to record in time and frequency domain. So you have the ability to check to see that all the signals are connected correctly. Once you hit the play or the record button, you can actually still monitor during the recording the operation of the signals to make sure that they're still present and valid. After the recording, you can use this utility to play the file and look at the file again in how it was recorded and look at all the data. So there's cursors, there's calculators for frequency and amplitude, harmonic distortion, for example, is calculated. And you can use this to look at any A to D converter or digital down converter output that's part of the system. We have a lot of different systems available. One class uses the 200 megahertz 16-bit A to Ds and either 800 or 1.25 gigahertz 16-bit D to As. So you can have up to 8 channels of either one connected in a chassis, connected through the system to a RAID controller, also with digital down converters and digital up converters as part of the signal path. So these come in different form factors, the commercial, the rugged, in the portable, and the rugged rack mount, and then at the lower right you can see the extreme, the RTX. Basically what we're doing here is we're taking exactly the same technology and same software, and we're just putting it into different form factors for the particular environment that it needs to operate. Another class of products is based on a 500 megahertz 12-bit A to D converter system that also includes 800 megahertz 16-bit D to As. So this again is a transceiver, 500 megahertz in, 800 megahertz out, with or without interpolation and digital down converted decimation. Again, the same kinds of classes of products as you can see down below, based on the same form factors we just talked about before. For people who want to go a little bit higher in frequency, we have a dual channel 1.6 gigahertz 8-bit A to D system that can record data in real time at 3.2 gigabytes per second. This is all in a 4U chassis. We use solid-state drives for these systems because the drives need to be fast. We can also take that same hardware and configure it as a single channel 3.2 gigahertz 8-bit A to D converter, again recording samples to disk in real time continuously at 3.2 gigabytes per second. And this basically allows you to start with an empty RAID array and fill it up to however many terabytes you need continuously without missing one sample at these very high rates of 3.2 gigabytes per second. Within probably a few months, we'll be over 4 gigabytes per second. The technology keeps moving, and we keep acquiring the new capabilities as we are able to get the newer technology. We also offer digital recorders. In this case, we have a 2-channel 10 gigabit Ethernet recorder that can use either copper or optical links on the 10 gigabit Ethernet, and we basically capture in the full-time, full rate 10 gigabit Ethernet up to 1 gigabyte per second on each of those 2 channels simultaneously, storing the data onto hard drives in that real-time rate. We have also recently announced a 8-channel serial FPDP recorder. Serial FPDP, also known as VITA 17.1, provides up to 8 links of either copper or optical serial FPDP traffic. These are excellent links between systems. They can go to distances as long as 10 kilometers with the optical single-mode fiber. And each of those links can operate at least 247 megabytes per second. so we can have up to 8 of those. We can actually operate at higher rates if we use a higher serial bit rate clock. So again, full recording, full playback, an excellent inter-system link, or just for moving data from one chassis to another. Again, available in several different form factors, serial FPDP. So just to summarize what we've talked about today, we're basically delivering high-performance recording systems, recording rates up to 4 gigabytes per second in a 4U rack mount chassis, PCI Express Gen 3 RAID controllers. We're using Pentec's Cobalt and Onyx. These are the Vertex 6 and the Vertex 7 software radio modules with PCI Express Gen 2 and Gen 3. And these devices allow us to get the data into the system fast enough to keep up with that front-end digitizing rate. For the inputs and outputs, we're doing analog recording currently at rates up to 3.2 gigahertz for capturing a 1.5 gigahertz analog bandwidth signal, a full bandwidth 1.5 gigahertz captured. We're also delivering D2A outputs at up to 1.25 gigahertz, gigasamples per second. And on the digital recording, as we've seen, 10 gigabit Ethernet and 8 channels of serial FPDP, which are nominally just below 2 gigabytes per second if you combine all 8 channels. We have storage capacities for magnetic drives in excess of 40 terabytes in a single 4U chassis, and solid-state drives in excess of 20 terabytes in a 4U chassis. Most of these systems, except some of the extreme systems, have all of the drive bays, all of the drives are removable through trays or drive bays, so that they can be removed and transferred over to say a lab system for processing or archiving after the acquisition is done. If you want to find out a little bit more about the recorders that we've talked about today, I invite you to visit pentec.com, our website, and click on the Talon Recorder Selector. It's a product selector tool that allows you to choose the parameters that are important to you up at top, and you can select, say, rack mount, 200 megahertz 16-bit, and 80 megahertz bandwidth. What will happen is the list down below will shrink, and you select the product that most closely fits your application. The more parameters you select, the shorter the list. And once you've got the model number that you're interested in, you can simply click on that model number, and it will take you to the product information page, where you can see data sheet, block diagrams, and get full specifications for these products. So just to summarize our presentation today, Talon Recording Systems really offer you multiple form factors for laboratory, office, portable, rugged, and extreme versions. And they're really complete instruments with analog and digital interfaces. They're fully programmable, ready to use out of the box. You don't have to do any software development. You've got those powerful tools like the signal viewer. And if you do need to integrate this into a larger system, we provide the API. All of these systems are fully synchronous across multiple channels in the case of a multi-channel application. Last but not least, all the files use the NTFS file system, the Windows native file system that allows you to open up the recordings after they're done immediately in tools like MATLAB, for example. So that completes our presentation today. I really appreciate your attention, and I'm going to turn it back over to Lee.
Thanks, Roger. So if anyone has questions for Roger on the presentation, please go ahead and use your question window, or else raise your hand and I'll unmute your microphone. The first question we have, Roger, is the RF front end protected against high RF signal levels when capturing data in the field near a transmitting tower?
Okay, we do have other devices that typically represent the RF tuner part of it that would translate, let's say, an antenna level signal frequency down to IF, which typically our recorders operate at the IF level. So there's typically something between our recorder and the antenna. So it would be a function of such a RF tuner block to do any analog protection for, let's say, lightning or high-frequency signals or some kind of a limiting device suppressor to protect against damage. So I guess the answer is, of course, you have to take care of that. And there's really two classes of problems. One is a very large signal that's just say next to a signal that you want to look at. In that case, you would need to have typically a filter. And some of the RF products that we provide now, we have a series of products called Bandit, which you'll also be able to see on our website, where we actually have what we call slot receivers that exclude frequencies above and below a particular slot. And so if you had a high interfering signal that was in an adjacent slot, we would attenuate that sufficiently so that you could get the dynamic range you need to see the smaller signal. So I'm not sure if I answered the question directly, but those are my comments.
Thanks, Roger. The next question we had, I think, is related. Is there any anti-aliasing filtering on the input?
Yes, the anti-aliasing filter is a function of, again, that RF tuner, if you want. So in any case, what we're doing is we're digitizing either baseband or IF signals. Usually, when we're dealing with an IF signal, we have the aliasing issue is taken care of because the IF output is typically band limited to the IF channel bandwidth. In the case of a baseband signal, however, you do need to ensure that you have a sufficient low-pass filter, let's say, before the A to D converter to avoid aliasing. Again, if you have the RF tuner block, this would be taken care of in the RF tuner. So, so to answer your question directly, our recorders do not have low-pass filters at the front end unless you've arranged to have a special tuner or filter put there. One of the reasons is that some customers want to do undersampling. Some customers want to do baseband sampling. So we can't really put a filter there that would prevent some customers from operating the recorders the way they need to.
Okay, thank you. Those are the only questions we have. Are there any other questions? Anybody wishes to raise their hand to ask a question? Okay, I think there's no more questions then. Oh wait, one more just came in. What's the lead time for ruggedized versions?
Typically 14 weeks is the lead time. So it takes a little bit longer. Most of the other products are 8 to 10 weeks, but 14 weeks. And again, this is for a more mainstream ruggedized version. If you have something exotic, then it's going to take longer.
Okay. One more question. Can you provide higher sample rates like 3.2 gigasamples, 12 bits like your SDR?
Yes, as a matter of fact, the A to D converter that we're using for the digitizer that I claimed 8 bits in is actually it's a 3.6 gigahertz 12 bits, and the only reason that we're limiting the capture to 8 bits is because of the current limitation of the storage rate that we have, which is 3.2 gigabytes per second. We're currently limited by that primarily due to the PCI Express interface across the Gen 2, which is the current interface that we're using. When we go to Gen 3 on that particular module, we will be able to get up to the higher rate of 3.6 and at 12 bits. So if you keep 2 bytes per sample, that's a 7.2 gigabyte per second stream. which is quite challenging. But with PCI Express Gen 3, you can achieve that. So I guess the short answer is not today, but it's coming soon.
Okay, thank you. Are there any other questions? When do you expect to archive this data rates? Is there a timeline for that?
Oh, excuse me. I would say sometime. In other words, the full
achieve these data rates.
To achieve, okay. Yeah, to achieve, okay. I would say sometime in third quarter, probably, is when it's most likely going to happen. The technology is evolving through our what we call our Onyx, which is a Vertex 7, and that board will be available during July, I believe it's scheduled for. Right after the board's available, we'll be putting it into a recording system and then pushing the data rate up as high as we possibly can. The goal is to go to the full rate at 3.6 12 bits.
Okay, thank you. Any other questions? Okay, we'll make that the last question then.
Right.
Roger, thank you again for your time in giving this presentation. If anybody has any additional questions, go ahead and feel free to email them to me, and then I will forward them on to Roger. And Roger, you can follow up via email. Is that correct?
Yes, I will. Be glad to. And,
okay.
And thanks everyone for attending. And thank you, Lee.
Sure. So a couple of quick announcements before we close. The forum will be announcing more webinars shortly. If you're interested in giving a webinar, we have a request for proposals open. You can go to wirelessinnovation.org, webinars_tutorials_resources, and you'll see the link for submitting a proposal to do a webinar there. We're going to be sending a link for a webinar satisfaction survey, basically to get your feedback on how this webinar went and changes we should be making in the future to make these more effective for you. And finally, if you have any questions, comments, or concerns, please feel free to contact me directly. My email address is lee.pucker@wirelessinnovation.org. Thanks again, everyone, for joining us. The slides will be posted later today, and you should be getting a thank you with instructions on how to download the slides then. Thanks, everyone.